Okay, the second part of today's lesson is talking about the molar enthalpy. And even when we are talking about molar anything, molar mass, molar anything, what we are saying is what is it? So what is the mass when we are talking about molar mass per 1 mole? Even on the enthalpy, when we are saying what is the molar enthalpy, what we are defining is what is the enthalpy per 1 mole of the substance that we are, or chemical compound that we are talking about. And if the units for the enthalpy are in kilojoules, then the units for molar enthalpy will be kilojoules per mole. Will be kilojoules per mole. Now, the delta is the change in this reaction, is the change of state, final minus initial. R stands for the reaction. Usually, if it is a combustion, then we say C. If it is a combustion, we say C. If it is formation, we say F, and so on. N is the number of moles. Of that particular compound that we have, and delta Rm is the molar enthalpy of the reaction. So delta Rhm, M stands for molar. Of reaction. If we take a look here on the units, then the change on enthalpy of the total reaction will be number of moles times kilojoules per mole. That is the molar enthalpy. So moles and moles will cancel out. So the change enthalpy of the reaction will be equal to or given into kilojoules. Okay, so let's see some cases in which we are dealing with this kind of formula, which is in your formula sheet. So 1.5 grams of ammonia undergoes a reaction. If the molar heat of ammonia for this reaction is negative 131 kilojoules per mole, determine the energy produced. So now we have mass of ammonia is 1.75 grams, and the molar heat of the reaction for ammonia is negative 131 kilojoules per mole. And we are looking for delta H of ammonia. So the very first thing that we have to do is we have to figure out what is the number of moles for this 1.75 grams of ammonia. And in order to do that, what we need to know is to convert mass into moles. Okay, how do we do this? By finding the molar mass. So let's figure out what is molar mass of ammonium. Ammonia, as we have mentioned, if you do not remember what is the formula for ammonia, then your data booklet will be your best friend. And in page 4 and 5, you can find the chemical formula for ammonia, which is NH3. That means that you have one nitrogen and three hydrogens. So then, in your page 1 and 2 of your data booklet, you can find that the molar mass of nitrogen is 14.01 grams per mole, plus the molar mass of hydrogen is 1.01 grams per mole, which gives you a total of, use your calculator and figure it out, 17.03 grams per mole. What does that mean? As I have mentioned even in class, we always will put a meaning into the numbers. So that means that 17.03 grams are in 1 mole of ammonia, or if you have 1 mole of ammonia, then you have 17.03 grams of ammonia. Now, in order to convert this into moles, what do we have to do is we start with what is given. So 1.75 grams of ammonia times, and then you think, what is the ratio that you have to multiply by to cancel the given units, the units of grams? And the answer will be is ratio 2. Why? Because grams on the given are in the numerator, so in order to cancel them, we need them to be in the denominator. Grams of ammonia and 1 mole of ammonia. So grams of ammonia and grams of ammonia are canceled out, and then in your calculator, 1.75 divided by 17.03 will be 0.1027 and so on, 59 moles of ammonia. And now, in order to calculate the enthalpy change of the reaction, we go with the number of moles, which is 0.1027 and so on moles, times the molar enthalpy of ammonia, that is negative 131 kilojoules per moles of ammonia. So then you even see here that moles and moles is cancelled out, times 131. And your calculator will be the change of enthalpy of the reaction for this type of reaction for ammonia will be 13. This is what calculator gives you, 4615 and so on kilojoules. However, based on what is given, you have to express your answer into 3 significant digits. So you have to stop here. So your final answer will be delta RH, and it is negative because negative is carried over, negative 1, 3 dot, and now you take a look at the consecutive digit, and then you see that it is greater than 5, so therefore you will round it up and will be 13.5 kilojoules. So this will be the how we calculate the enthalpy of the reaction when we know the molar enthalpy. Let's take a look now to this example when we have a 0 point mass, when we have mass of methane. Methane is in, even if you can see it in your, if you don't remember, in your page 4-5 of your data booklet is CH4 is 0.320 grams. Undergoes a combustion, producing a heat. So the heat of the reaction is 17500 joules. Calculate the molar heat, so of methane, CH4, CH4, you can write it here or not, whatever you want. So now the molar heat or the heat of the reaction, it will be number of moles times the molar heat of combustion. In this case, this is why I'm writing C for combustion. So from here, the molar heat of combustion for methane will be whatever is the total heat of combustion divided by the number of moles for methane. So then this formula dictates us that the very first step that we have to do is to convert grams into moles. So in order to do that, we have to identify the molar mass of methane, which is 1 carbon plus 4 hydrogen, which is 1 times 12.01 plus 4 times 1.01. So this will be 16.05 grams per mole. What that means is that if we have 1 mole of methane, then we have 16.05 grams of methane, or if we have 16.05 grams of methane, then we have 1 mole of methane. Now we start with stoic, gravimetric stoic, so 0.320 grams of methane is multiplied by a ratio of 1, and in this case we have 2 ratio 1, and ratio 2. So you'll have to ask yourself, saying which ratio are you using, ratio 1 or ratio 2, so that whatever the units of given, in this case grams, is cancelled out. And then you will have to apply ratio 1. Then, therefore, you find the number of moles as 0.019937 and so on, moles of methane. Now that we have moles of methane, we find the combustion, the molar heat of combustion for methane, which will be 17500 kilojoules over 0.019937 moles. And then using the calculator, you will have, so the calculator gives you 877.734. This is joules, not kilojoules. Okay. This is joules. And 734.375 joules per mole of methane. So first we convert it into kilojoules. So this will be molar combustion of methane will be 877.734 kilojoules per mole of methane. And now we deal with the correct index, which is 3. So this will be 878 kilojoules per mole. So the molar heat of combustion for methane is 878 kilojoules per 1 mole of methane. Okay, so let's take a look at another example in the same kind of formula. I would recommend that you stop now the video and then try to complete your work on your own. However, and then check after it with my work here. But if you feel that you are having difficulties on it, then please go ahead and watch the video and then try it on your own. So now we have paradichlorobenzene undergoes solidification, which you know that is a phase change from liquid into solid, and the heat of solidification is 9600 joules, which I'm converting it right away into kilojoules, so 9,600 kilojoules. Determine the mass, so mass is question mark, used if the solidification molar heat of combustion will be negative 320 kilojoules per mole. So the very first thing that we have to do is we have to find the molar mass. And from the formula, we see that we have 6 carbons and 4 hydrogen and 2 chlorine. Then we go to our page 1 and 2 on your data booklet, and then we figure out that we have 6 times 12.014 carbon, 4 times 1.014 hydrogen, and 2 times 35.45 for chlorine. So let's find the molar mass of paradichlorobenzene and then complete the steps. So the molar mass of paradichlorobenzene is 147 grams per mole. The meaning of it is that if we have 1 mole of paradichlorobenzene, so C6H4Cl2, then we have 147 grams of it. Or if we have 147 grams of, then we have 1 mole. Okay, so now, based on the formula, the heat of reaction will be moles. The heat of reaction will be, and it is solidification, number of moles times the molar heat of solidification. So then from here we find that number of moles will be the total heat of solidification over the change of enthalpy for molar mass, or 9.600 kilojoules over negative or 320 kilojoules per mole. So kilojoules and kilojoules is cancelled out, and then in your calculator 9.6 divided by 320 will be equal to 0.03 moles of C6H4 chlorine 2. Now, knowing the molar mass, we complete stoic and figure out the mass that is undertaking into this reaction. So, starting with what is given, moles of C6H4Cl2 times which ratio are we using, ratio 1 or ratio 2? We will use the ratio that will cancel the units that we start with. So in this case, it will be ratio 2, 1 mole of C6H4Cl2 will be 147.0 actually grams. So moles and moles is cancelled out times 147, then we will have 4.41 grams of C6H4Cl2 that is being part of the reaction, the solidification, which is releasing a 9.600 kilojoules. Okay, I hope that this makes sense. I will stop here this part of the lesson and then we'll continue with more parts. Okay.